Hello, everybody. Welcome to my fourth talk about Kryptos K4. Today it's going to be a set of slides about the technical aspects of Kryptos, and then more about the people, the history, and the artistic aspects after that. So let's begin with Tintin, the famous comic. In one of the books, Seven Crystal Balls from 1943, there's an expedition of archaeologists who go to South America and they dig up some mummies. And as soon as they get back to Europe, they're struck by a mysterious illness. Everybody starts falling into a coma. And the detectives are talking about it to Tintin, and Tintin says, "Oh, well, this is all very strange, but in the end, it could be a mere coincidence." So Tintin uses his gut feeling to try to diagnose what's happening here, whereas a professional medical doctor would use a series of tests, and that they'd work with other people. They wouldn't just try to come up with something by themselves in a difficult case. And the detectives insist that it's more than a mere coincidence, and Tintin says, "Well, how can you prove it? And first of all, let's try to work out what it is. What is this mysterious illness?" Now let's just have a look at what I've been doing since the last um, talk I gave about Kryptos. So I published my crypto diagnosis of K4 paper in the Historical Cryptology Conference proceedings in 2021. In August, the one of the three solvers of Kryptos in 1992, one of the NSA employees pictured here, died at the age of 81. The same month, I solved a Porter cipher published in those Histocrypt proceedings, an alchemical cipher, and then a bit later I published my most recent talk about K4. In 2022, Frank Rubin published his book Secret Key Cryptography. You can get it there as an ebook. And also throughout the year, Moshe Rubin published some very useful cryptography books to the Internet Archive, Elementary Cryptography and Cryptanalysis, The Cryptographer's Way by Bradford Hardy, who was a key source for David Kahn's The Codebreakers, and Solving Cipher Problems by Frank Lewis, which I found quite difficult to get hold of a few years ago. In the middle of the year, GPT-3 came out. I thought I'd try to use it to create an English text that could be a solution to K4, given the constraints that you had to have east, northeast, and Berlin clock in some places. Obviously, AI is very useful, but it's banned from the Reddit codes community for good reasons, because irritating people come and post, "Well, I think I've solved this or that cipher," and they can't explain what they did. So they're suffering from the Dunning-Kruger effect. They're incompetent and unaware of it. And even as of 2024, like 2.5 years later, we can't really get ChatGPT to come up with an answer to that problem without a lot of guidance. In the middle of the year, I went to Amsterdam. I gave my Histocrypt talk on K4. Magnus Eckel told me about the concept of pre-whitening as a K4 hint. This is a word that John Tukey invented in 1956. It was used by Martin Hellman to describe DES in 1979, and then used later in a cryptographic context as just the word whitening. But obviously this hasn't proved to be a particularly useful hint. I visited Canberra, this sculpture up here. called Encrypt, which is lots of pillars, which is clearly inspired by Kryptos. It's outside and really accessible. It's obviously been sculpted with meticulous care. I went to the National Library of Australia and I read David Schulman's annotated bibliography of cryptography, his 1976 magnum opus, which lists books about cryptography from, starts about the year 1400, 1500, and up to about 1973. September, the ebook Apprehended by Bill Bonk was published, and you can read about the Handman book cipher there, which comes up a little bit later in this chronology. 2023, the NSA Dragon Seeds newsletters were published on the Government Attic website, and there's a slide about that a bit later, describing how diagnosis works. So finding from just ciphertext what the cipher type was and things like that. I bought a guidebook for Berlin up there, published in 1991, before Kryptos was a thing, or the keywords had been released, and you can see it's got nice yellow and red cover colors, and it does describe the three main clocks that Sanborn mentioned as possible Berlin clocks. So the set theory clock, the world time clock, and the clock of flowing time. So they were popular at the time. Kryptos was put in place at the CIA. David Vieira solved the famous Richard Feynman ciphers that were published in 1987. He was helped by AZ Decrypt. You can go and read about how he did it at Reddit. I went to Histocrypt in Munich, and I went to Berlin for a day to visit the clocks. So there's the set theory clock, the world time clock, the town hall clock, and the clock of flowing time there. And the most popular one by far is would be obviously the world time clock. But when you compare the set theory clock and the clock of flowing time, I'd say that the clock of flowing time gets about 100 times the visitors. Everybody just walks past the set theory clock. Over a long period of time, I edited Ed Scheidt's English Wikipedia page quite a bit, so we'll talk about that a bit later. And on to the current year, I hassled Rob Simpson at the National Cryptologic Museum to publish David Schulman's supplement to an annotated bibliography of cryptography, and he's made that available there, so you can see cryptographic books from about 1973 to 1985. That might be useful for seeing what sort of things could have inspired the Kryptos K4 algorithm. And finally, in March, the Z340 solvers finally published their paper about how they did it. You can read it on the archive. The Kryptos Society newsletters, that's a cryptologic society at the NSA, was published on the government attic. And two interesting things for this talk would be the principles of diagnosis, the 12 principles, and a reference to the Handman cipher right next to Kryptos. In May, a guy called Lemino published his Kryptos video. It's up to almost 6 million views now. In June, with Louis Helm, I solved a 24 and 22 letter Playfair challenge from a couple of years back from Claude Schmet. I learned some things about large language models. A crucial element was using a language model from 2014, which was about 6 terabytes in size, long before AI slop was around, and and all the text started getting poisoned by references to Berlin clocks and AI generated text. I used um, 8, 9, and 10 gram statistics, but none of it was any good. Christian Schrid wrote about Ed Scheidt's driveway. It's got some Mayan symbols in it. He wrote a blog about it. And then most recently on the Reddit codes community, the 26-letter cryptograms of Lambros Kalamahos. He's the NSA famous cryptographic teacher. They were solved by Yefim Shifrin. Okay, so that's the chronology up to date. In the meantime, I have tried very hard to solve lots of other ciphers and things that I thought were going to be dead easy, and I've completely failed on a lot of things. I remember sitting in the audience at Histocrypt in I think it was in Munich last year, and Cosimo Palmer stood up and gave a talk about this inscription you see over here in the Turbolo Chapel in Santa Maria la Nova in Naples, and the index of coincidence was just like a European language, and it has a Latin inscription right next to it. It's got spaces, but no one's been able to work out what it's about, which is very frustrating. We don't know what's going on. There's a Werner Oswald telegram on Cryptiana. Klaus Schmer also published on his Facebook page. It should just be Spanish language text with transposition, but I haven't got anywhere with it. This is a kind of alchemical cipher called Thorough Summary of All Celestial Influence. Obviously, George Lasry and some other people have taken a look and haven't got anywhere. Again, looks like a monoalphabetic substitution, but nothing works. We've got this bell here right behind my head, the Rudolph II, Emperor Rudolph II, the handbell cipher. Got an inscription on in the middle of it. Looks just like a so-called key phrase cipher, but I've been unable to solve it in any European language. This so-called key phrase cipher has been seen in the year 1649 and also in the year 1832, and that's about it. It's not a popular cipher. I looked at the Hantman book ciphers. I tried to use mountains of dictionaries and the KenLM language models. Nothing worked. I looked a bit at Encrypt, the unsolved Vatican ciphers, and various other chemical ciphers, but I haven't got anywhere. Let's go back to Kryptos K4. There's a thesis about it for a Master of Science in Maths. It was a prize-winning thesis in 2012 at Texas Tech. And one of the ideas she came up with, a lot of other people have looked at it, is that if you were to consider that K4, the fourth part of Kryptos, is working in the same way as K1 and K2. So it uses the Kryptos alphabet as a plain alphabet and as a cipher alphabet, then you can derive an implied key, because the word Berlin is supposed to encipher to NYPVTT. And if you use the same methods that were used in the previous parts of Kryptos, that implies that the key is ELYOIE, which does look like transposed English. So what she did was she ran a chi-squared test just on that small amount of non-plain text to try to see if you could rule this key fragment being English in or out, and she was saying, you can't rule out that idea. Um, the funny thing was what you see on the sculpture is something which you don't see anywhere else. You see the plain alphabet being standard alphabet A to Z. You see the key alphabet being the letters A to Z, but then you see the cipher alphabet in the middle, the meat of it being the Kryptos alphabet. So you've got you usually have plain plus key equals a cipher, but they're in different alphabets here. So if you were to use the plain and the key from English text, what you see in the K4 ciphertext letter distribution is exactly what you expect to see, which is very interesting. What other people from the NSA solvers time onwards have noticed is what you see here in the block of text. You see that, sorry, that way. Oh, I'm confused. You see Kryptos around the edges of the sculpture there. So I've written it in a fixed width font, but it just does seem like that is more than a coincidence. But the question is, what sort of enciphering process or algorithm could have allowed them to do that? And if you used a transposed English key in this way, I would think that does make it easier to place those letters in those positions. So, for example, with Gromark, a more complex algorithm, that would be a lot harder. So that's also a good argument against Gromark being the cipher in use. And if you were to use a running key cipher, so that means you just have like plain English text as the key. There are two good papers about that, one by Griffin and one by Reddy and Knight, published in 2012. And Reddy found that 100-letter ciphertext could only be solved about 40% of the time. And that's without transposing any of the English text. So if it's just some random text taken from a book and then transposed, we're very unlikely to be able to solve it with either of those methods. So going back to the Dragon Seeds newsletter for some inspiration about the diagnosis process, there's a class, or there was a class called Practical Diagnosis at the NSA to diagnose non-crypto systems. So you go through an iterative process, you gather the information, separate undifferentiated traffic into homogeneous sets. We don't need to worry about that with K4. You make hypotheses after doing analyses, you test and prove them, and then the last step is writing the solution report. And we have a 12-step process on the next slide, which is a bit more systematic from the Kryptos Society newsletter. You look at the data, let it tell you what to do. Diagnosticians don't know what they're doing, and you must measure any phenomena you try to see. So you try to determine the significance of your answer rather than use your gut feeling. You should know the quality of the data, and you should believe in yourself. You should work as a team. You should cooperate, share data, and then the last step is the same as the 5-step process in the previous slide, document and publish. So in the last talk I gave, and at Histocrypt in Amsterdam, I talked about Gromark being a possibility for Kryptos K4. So what is the traditional Gromark cipher? So it's Gronsfeld with running key, the RK. So as I said, running key is just where you have a block of English text used as the key and it doesn't repeat. But with Gromark, it's a running key system, but you use numbers rather than letters. You generate a long key by starting with a primer, and then you use that primer to expand to the length of the text. And you use something called chain addition, modulo addition, using modulo 10. And This idea is used, since the beginning of World War II, at least by the Soviets. It's used in the VIX cipher described by Khan, and you can see modulo edition in this book, Spy Catcher by Peter Wright. And the traditional version uses a plain alphabet of A to Z, and the cipher alphabet is derived from a keyword. And this was described by someone called whose norm was Dumbo in 1969, and also by Kallamahos in 1977. So one question is, how close could K4 be to traditional Gromark? And if you looked at a cipher text and you found the index of coincidence was very low, so here it's 0.036. That means if you did a histogram and you plotted the frequencies of all the letters, it would be very flat. And an experienced cryptanalyst would say this is obviously not pure transposition. But the question is, like, how close could we get to meaningful English text if you just broke all the rules? You said, well, I need some English text, some meaningful English text with that index of coincidence. And one way to do it is to just combine pangrams, which are short sentences which use all the letters of the English alphabet. So, for example, if you say 5 quacking zephyrs, jolt my wax bed, sex prof, here's back quiz, no quiz with mild joy, Schwarzkopf, vexed Iraq, big time in July. It's 97 letters and it's got that index of coincidence, but it's rather meaningless English text. The informational content is very small, and there are very few sentences you can combine to get that sort of index of coincidence. So this is not choosing the explanation that best fits the data. In general, 97-letter sentences or blocks of text have 9 to 34 words, and the lengths will follow a Weibull distribution if you're interested in that sort of thing. With this book here, Can You Crack the Enigma Code by Richard Belfield, it had some challenge ciphers at the back. They challenge you to win an Enigma machine back when those things were rather more available, I suppose. And it turned out that the challenge ciphers used pangrams to lower the index of coincidence artificially down below 0.05, which means they tried to flatten out the frequency in the text. So they tried to make it much more difficult for the solvers by making artificial changes. And so you can also have very weird text like this one on the churn algorithm webpage, junk jewelry, jingles, jolts, dirty jackanapes, and so on. The index of coincidence is similar to what it is in English text, but the sentence doesn't really make a lot of sense, and you'll have a lot of trouble solving that as English text as a cipher challenge. So looking at that data for K4, we can say this is not transposition. It's not Playfair, the famous cipher using a 5x5 square, or seriated Playfair using different pairs of letters to Playfair. And I don't think you would have been able to create those letters on the edge of the sculpture in that way. It just seems impossible to me. This famous book, Cryptanalysis by Gaines, she suggested when you do see a flat frequency, a low index of coincidence, that may indicate a combination of transposition and substitution was used, but I don't think that is what's happening. based on my Histocrypt paper. And the reason is that when you compare the plain and ciphertext letters, there does seem to be a one-to-one correspondence. Sanborn's provided 24 pieces of information with those letters, but it's possible that when you consider them in pairs, that there's actually 276 new pieces of information, and you also have this information about where these plain texts are, and possibly since the the hints start at positions 21 and 63, it's interesting that they're both multiples of 21. Okay, so talking about pairs of plain text letters, the question is, what pairs of ciphertext letters do they map to? So if you assume that you're using the plain and cipher alphabets A to Z. So what I look at and what I notice is that when you look at pairs of letters which are close in the plain text alphabet, the distance between the letters in the ciphertext alphabet is also very small. So if you look at plain text letters that are the same or one apart, like, for example, the B from Berlin and the first C from clock goes to N and M, the ciphertext letters are one apart. And the B from Berlin and the second C from clock goes to NP, and that's two apart. So there are 34 pairs like that. If you sum all those distances, you get to 128, which is an average of 3.76. And if you were to, randomly permute the ciphertext that corresponds to east-northeast Berlin clock, you only get a number that low about 1 in every 5,000 times. And if you were just to look at the distances that were less than or equal to 3 or 4, instead of the mean, that would be a 1 in 35,000 observation. And yeah, so what does that mean? That's the question. You don't see that such a strong pattern when you're just permuting the plain text and ciphertext alphabets. So when the plain text difference is 0 or 1, we see the ciphertext difference being 0, 1, or 2, or 3, 23 times, which is extremely uncommon when you consider permutations of the ciphertext. And the pattern doesn't occur with just the Berlin clock hint alone. So as you can see in the screenshot there, the last one, positions 70 and 73, you've got C and C and the ones in clock, and they correspond to M and P, which is a difference of 3. So they're all very close. So to draw you a diagram, if I sorted the plain text letters, the non-plain text letters into alphabetical order, you can see that they're all very close, those highlighted yellow ones, from when the plain text is L to T and when the plain text is A to C. They're all in a very small range, and that F and that Y really stand out. So you really improve that observation if you wrote MZPFK for clock instead, and then you get that adjusted version there. You'd get the MF over there on the left and in the blue, and you get the QP there in the blue. So here's some text about how to generate a pseudo-random key, like you might do with Gromark or with Autoclave. This is from a lecture called A History of US Communications Security, and the lecturer talked about the principles being Fibonacci, Kochen, and Kokenacci, and there's an explanation of what a Kochen machine is. It's getting a little bit further away from simple pencil and paper ciphers, but that is what Gromark is doing. It's creating a pseudo-random key using pencil and paper methods. if you search for Autokey on the CIA reading room website, there's a document from 1976 examining the KG-84 cryptographic system from the NSA, and it mentions the auto key features of the system and these code words, Henley and Seville, if you want to read a bit more about it. So, based on this, Ed Scheidt would of course have been quite familiar with the concepts of auto key ciphers. So, getting back to the how close to traditional Gromark can we get? Like that, there's an example of how Gromark actually works using the keyword enigma, creating a particular alphabet in that order, and I won't go through that. But here's Gromark explained by Kalamahos, as I said before. Here's a way of creating a pseudo-random key using that rule. You can start with a keyword, or you can start with a 5-digit number like you do in traditional Gromark. And if you were just using A to Z as your plain alphabet, you can get 21 out of the 24 letters by just using the numbers 0 to 9. So for example, here over on the left down the bottom, we've got E going to F. You've got E and F directly on top of each other with the number 0 there, and you can use very small numbers to map East, Northeast, Berlin clock to the plain text. But you can't do this with traditional Gromark with the plain text A to Z, because you're going to run into problems. You have the ciphertext letter P, which needs to map to both C and R in the plain text alphabet, but they're 11 apart. So you've got the ciphertext letter K, which needs to map to both A from the east and northeast, and it needs to map to the K in clock. And so it's just not quite going to work. You'd need to have the base at least 12. So it doesn't look like, a variant of traditional Gromark. And so that leads to the question, how is the method so simple that you can get those letters on the edge of the sculpture at certain locations? And another observation made by Greg Materna is that the plain text letters, Kryptos, don't appear to move very much. And that's also about a 1 in 5,000 observation. So we go back to another cipher, which is a lot more complicated, called Autokey. That's where you use either the plain text or the ciphertext as the key for the cipher, with a bit of a shift. So those are the two major variants. And can you use PTAC or CTAC, I'll call them. So if you assume that the plain text alphabet is the ciphertext alphabet is Kryptos, as you did in K1 and K2, you get that implied key there beginning with RDUM. Is there anything unusual about that? I think unless Sanborn has chosen particular positions to give a certain pattern, you should basically be expecting random text there. You've got 10 out of 24 letters from the 7 letters of Kryptos, whereas if it was random, you'd expect about 6.5. That's not uncommon. What is unusual here is if you turned each of these letters into a position in the Kryptos alphabet, numbering them from 0 to 25, you only get 224. But if this was random, it would sum to 300. And random English text would sum to about 247 on average. So if you call this the K-sum, we'll try to talk to ChatGPT about getting a visualization of how rare that is. So I asked ChatGPT, if I pick 24 random values, how rare is it if the sum of the values is 224 or less? Give me a plot. And here is the plot. something like a nice bell curve. And there's the red line to show you how rare that is. It is quite rare for them to be 224 or less. We'll call it the K-sum. It occurs in less than 2% of the cases in that simulation. Okay, but there's no reason it should not be random. So the ciphertext is this set of letters presented here. The K-sum is 252, which is in the top 10%. And if you applied that sum to the whole ciphertext, it would be in the top 13%. It's a weird plain text. It's got lots of cryptosy letters in it, like, you know, ST, ORT, ST, ROK, that sort of thing. So it's in the top 10% of English texts in that sense. The really interesting one is, although this is just what we've been talking about, is the implied key using the Kryptos alphabets. So, as we said, it's in the top 2%. It doesn't look like random text would be likely to produce this pattern. We'll say it's very cryptosy. And what could produce that? Christine Seaman suggested, you know, this could be transposed English, but if you apply a chi-squared test, you know, you've got lots of unusual things happening here. You've got 3 Ys, you've got 2 Ks, and you've got a Q. And if you were to pick 24 random English letters, that doesn't happen very often. It's quite rare. But if you were to pick, say, a 97 letter source with lots of Ks and Ys, he says, I know what you're thinking, you're asking yourself, that sort of thing, then a 24 letter random sample will be quite likely to have those properties. I've looked for 97 letter samples from large corpuses of English text, and for that pattern to occur, and you know, the best I've been able to do is 22 out of 24 letters there. Okay, and right, this pattern is seen in both the east, northeast, and Berlin clock cribs. So this K-sum is very low in those, which is quite different to that other observation I was making about the correspondence between the plain text and ciphertext letters. So this is quite interesting. If you were to compare just the even positions in that implied key, then you get an even stronger result. At worst, you know, 1 in 630 after looking at some random permutations of the plain text and ciphertext. And you really wonder what is going on here when you take these letters R, U, R, Y, O, N, Y. The sum is very low. So some ideas are that you could be somehow getting an English sentence and applying some sort of transposition to it. You could be using something like the linotype alphabet, which begins with the most frequently used English letters, E-T-A-O-I-N, and doing some substitution, and then the most frequent English letters will go to letters at the beginning of the Kryptos alphabet. And, you know, other people have noticed that there's something unusual going on there too. So Hamid Samak noticed that if you just look at E-Y-I-C-A-K, it looks like letters from the word gimcrackery as a rotated keyword, and that does come up a lot when you're looking for this pattern in English text. So if you just ask ChatGPT the same thing about the English text from the alternating positions, it says, you know, this is very rare. It only occurs in 0.6% of random texts. Okay, if it's a real pattern, what could it mean? Here's a quote. Ed Scheidt said the systems used in Kryptos were classical cryptography, nothing weird. Question is, could it be just pure auto key with random alphabets or alphabets derived from keywords? How could we ever find that if that was the case? I think it's a bit unlikely, but here's some ideas. If it's just classical cryptography, ciphertext auto key with two unknown alphabets, it doesn't work at lots of widths. If it's plain text auto key with two unknown alphabets, it works at a couple of different widths, starting at width 5. We could alternate PTAC and CTAC, or we could force one of the alphabets to be the Kryptos alphabet. We could do with a lot of different things. So if we force the plain text alphabet to be the Kryptos alphabet, and then we choose a primer of length 12 at the beginning, you can try to look for a ciphertext alphabet that gives you those east, northeast, and Berlin clock cribs in the right place and makes the rest of it look like English, and you can do it. But then you go back and it gives you a primer at the beginning. And in a lot of those cases, you find that that primer that's implied is not credible. It's got nothing to do with English. There's a few other ideas here. You could turn Kryptos, the keyword, into an alphabet in a couple of different ways. Ed Hannon suggested that way. You could force the plain text, the plain and the cipher alphabets to be the same, one to be the reverse of the other. You could try to put a primer word before in the auto key, but then I don't think you'd be able to solve it. I don't think it would converge. If you picked a primer length 7, what you see is that it forces lots of other letters in the plain text. You could do really weird things, very long primers. You could have it go right to left, not left to right. Here we go for the plain text ideas again. There's Frank Lewis's book, Solving Cipher Problems. He warns you that plain text auto key is extremely error prone. An idea is you could have the text in a matrix, and then you could permute or transpose the matrix somehow, and then that permuted matrix could be the key. But it would be very tricky to get that to work on pencil and paper, and it's already very error prone. It's a possibility, but just very unlikely. So with plain text auto key with primers of various lengths, it forces lots of other letters in the plain text, no matter what plain and cipher alphabets you choose. So if you had a primer of length 7, then it forces all of these other letters in the plain text. So here's a little diagram of what happens. You get above east, northeast, you get O and 5 unknown letters in the C, which could be something like Olympic. And then after Berlin clock, you get 3 unknown letters and then a K, something like that. But you can try to use Louis Helm's statistics to try to work out what the rest of the plain text is, but just seems really unlikely. And if it was auto key, can you solve for plain and cipher alphabets simultaneously? The common software, AZDecrypt, CryptoCrack, Cryptool, there's nothing in it that would solve auto key in this way. I just don't think it would converge. I can get Gromark and Digraphid to solve like this, but the problem is if you make a small change to the plain or cipher alphabet in an auto key cipher, you can get a huge change in the implied plain text. So any kind of letter permutations or swaps are not very effective. Okay. You could take two keywords, and you could produce two alphabets, one plain, one cipher, using transpositions, but I can't see a way of solving that without trying all pairs of keywords. Um, and in the back of your mind, you're saying, look, I've seen these patterns where the plain and the cipher letters are very closely corresponding, and you've got that Kryptos pattern on the edge of the sculpture. Would you really have been able to do this with a really complicated method like this? And I think the answer is no. So just a quick review of famous cipher challenges before we go on to the people and the art section of this talk. So we had John Byrne and his chaos cipher. Published a book in 1953 with a couple of challenge ciphers in it. Nobody knew what to do with them because he wasn't saying what the algorithm was. Louis Crew and Cipher Devoise published their own challenge, but they made some mistakes in their chaos cipher challenge. So they did things like swapped O's and D's around, swapped U's and V's around, which made it completely impossible to solve. And a group of three people found the printout of what they intended to do with the dot matrix printing in the National Cryptologic Museum about 24 years later. And then they were able to publish a paper saying, it would have been impossible to solve this. Lasry, Rubin, Capel, and Wacker found a solution through a brute force search in all the books of Project Gutenberg and discovered more transcription errors, even though Crew and Devise said encipherment was done by a computer and can thus be considered error-free. So you've got cryptographic experts publishing a challenge and then never went back to check it, and it was completely impossible to solve with such a complex algorithm. So as I said, last year, the famous Feynman ciphers were solved with a bit of help from AZ Decrypt, and it used a very unaesthetic cipher. Some words were, a substitution, and the alternating words were a substitution with the words backwards, and it just doesn't seem like it could ever have been solved manually as it was intended. I think it was created, sometime around World War II. You may remember the famous code book from Simon Singh with 10 challenges of increasing difficulty, and number 5 was a book cipher. Hard to say whether that was fair or not, but he did give out some hints on the way. I've mentioned the Belfield challenge ciphers. The decipher puzzles were another book cipher in the 80s, which was really quite impossible to solve without knowledge of the key, and the book really could have been anything. Jim Galogli set some challenges in 1999 with some double playfair, and then after he gave out the ciphertext, he realized that he needed to give a lot more hints, and really still wasn't enough for anybody to be able to solve it. As I mentioned, Klaus Schmer gave some playfair challenges of length 24 and 22 letters, and it just turned out to be a huge step up in difficulty from his previous challenges. And you could actually find a lot of phrases on the web that could be solutions to either of those challenges. And so what happened was I submitted like large numbers of solutions and said, is my solution in here? So it was like giving lots of solutions to Kryptos and saying, well, tell me, is the answer in here? Call of Duty Zombies computer game has lots of challenge ciphers, and they've used all sorts of things from the ACA, the American Cryptogram Association, Morbit, AMSCO, fractionated Morse, and even Purple It's quite impressive. It does lead to the familiar questions like, are there hints about what the cipher types are? And can you diagnose a rare cipher type from only ciphertext? You know, and the answers to those questions are still quite open, but it gets a lot of people into classical cryptography who otherwise wouldn't be interested. Okay, so that's all the classical cryptography stuff. Now we move on to discussing the people and the art. Okay, so Berlin clock was the non-plain text for Kryptos K4 in 2010 and 2014, and the interesting thing is you've got a picture of a Berlin clock, one of the original Binninger ones there, with the yellow and red lights, but it wasn't his only clock invention. So he invented a backwards running East Germany clock, which became a bestseller there. And there's a copy of a picture of a patent that he wrote in August 1973. The idea is that this kind of clock was going to be very useful to read from a great distance at night. So yeah, it was really better in its original location on the Kurfürstendamm rather than sort of tucked away in a corner where it is at the moment. There's an article in 1989, John Le Carre. Obviously, he's referring to Sanborn, saying Sanborn needs help designing a piece of sculpture for the CIA headquarters in Langley, but that didn't eventuate, I don't think. It doesn't say it didn't happen, but I don't think that K4 was written by Le Carre in the end. One thing I've always found interesting was Ed Scheidt's biography on the CIA webpage. It says a few things like in the 1980s he became a communications security officer. It doesn't say, he was the head of a or the cryptographic center, which is what was said later. And it also said, more interestingly, that he contributed to cracking codes in the academic world, and he helped break a manuscript about a distillation process. And then it says it's very flowery, and it says he guided the translator to what he thought was a methodology that provided the key. And I wondered for a long time what that manuscript could possibly have been. And recently there was a paper published by Seth Rasmussen called Distillation and the Isolation of Alcohol, with a list of all the manuscripts about this process. And there's only one enciphered manuscript in it called the Mappe Clavicula. But if you look over here on the left-hand side, you'll see that this is just a monoalphabetic cipher. Like it's a Caesar cipher where you just shift each letter one. So the Latin XKNK just goes to Vini, VINI, and QBSUF goes to PARTE, and so on with some errors. And so it's really perplexing, like why he would mention that. Yeah, I think surely he had some better stories, so that's really perplexing for me. It's weird. Then we go off on a bit of a tangent here. There's a CIA webpage. There's two there with the same text. It says this machine was developed by the Dutch to communicate banking secrets. And I mean, you don't need to know very much about the Enigma to know that this is complete rubbish. But there it was in the 2007 front page featured story. And unfortunately, this claim is now cited in published books. Like there's one in 2019, and it's a real pity that that this was published, and there's very few ways to communicate with the CIA and tell them you've got it wrong. There was a paper published in 1999 in Cryptologia saying, this is how the error arose. There's the author was the inventor of Enigma was Scherbius, not Koch. Yeah, that's quite disappointing. So don't just believe anything you read on the CIA webpage about encryption. So after Scheid left the CIA, he founded a company in 1999 called TechSec, and here we go back to the first TechSec page from 1996 on the Internet Archive's Wayback Machine here. It said Mr. Edward Scheidt's years of government service culminated in a position as chief of an organization within the intelligence community which focused on cryptography and key management issues. Then you go over to the software page and they talk about a few different algorithms, and they've got GOST, G-O-S-T, the Soviet algorithm misspelled as ghost, which is not auspicious. They talk about triple DES as DES triple, and then they talk about something called P2, which is supposedly TechSec's patented high-performance cryptographic algorithm, which sort of takes you down another rabbit hole, I suppose. Does knowing what it is help you with Kryptos in any way? You look at the TechSec page from 1999, and it says he's chairman of a cryptographic center, and then in the same year, he's sort of been promoted to head of the cryptographic center by Jim Galogli here, and up in Computer World and in the Washington Post over there. It's quite a promotion. Nothing in the CIA biography like that, but there it is in all these articles. Here's the P2 patent. The question is there anything novel happening here? And it's not a very exciting read. There's a lot of repetition. There's no pseudocode of what the algorithm is. There's no details. It's more like he's patenting a set of ideas or a framework or a concept. And there are a lot of other cryptographic algorithms like SEAL, RC5, RC6, IDEA, RSA, where if you go and look at the pattern, you can know how to implement that algorithm. So you wonder if this was actually patented to try to capture a whole set of ideas and gather income that way. So is there anything possibly relevant to Kryptos? So you see the ideas of layers of encryption, of additive transformations, permutations, modular arithmetic, prime numbers, a bit of that. And it uses key escrow. So that's protecting a key so that law enforcement can decrypt something if they really want to, if they have the need. Something even weirder is a couple of years after that, on the NIST website, someone never heard of before or since, Kevin McGowan, wrote in something saying, you should consider P2. It looks like marketing speak. Extremely high performance, cutting edge, strongly feel. There's nothing technical in here. There's no technical argument. This is a good algorithm, and nobody even knows how it works. And the AES, the Advanced Encryption Standard, had already been selected 6 months before this. So this email is really weird. I would say that this looks like sock puppetry for TechSec, trying to just drum up business for them. It's really weird. Was a book called One Jump Ahead about computer checkers, first published in 1997, and in the revised edition in 2008, the author claims that Ed Scheidt's father was the famous FBI agent and checkers player, but that's not actually true. So this is the source of a lot of misunderstandings later on the internet. And then we have another quote about the deep throat of codes. Um, the CIA chief William Webster actually called Scheidt the wizard of codes, but then we got this process of Chinese whispers and my 2015 on the TechSec website they described uh, you know William Webster called Ed Scheidt the deep throat of codes, which is pretty funny. On the Wikipedia page for 7 years, it said Ed Scheidt's birthplace was Santa Monica, but what actually happened was that this was inserted by an eccentric Kryptos fan to match Ilonka Dunan's birthplace of Santa Monica. So the lesson is here, whether it's the CIA website or the Wikipedia website, you can't believe anything you read unless you can verify it from some completely independent source. Here's another sculpture called Antipodes by Sanborn. It's like an accessible version of Kryptos in Washington, D.C. I think it's slightly shorter and it doesn't have that verdigris with that green copper. They fixed some of the mistakes. Like I said, the header rows in the encryption table are removed. They were mistakes. That pattern in the K4 ciphertext is not there. Interestingly, people have said, maybe it's called Antipodes because there was a Thomas Jefferson cipher that used Antipodes and artichoke as keywords. And that would seem to fit the Kryptos design criteria that it has to have identifiable American roots. But actually, there's a quote here at the bottom from Sanborn explaining why it's called Antipodes because of the two opposing screens. And he mentions that, having it on the mall between the Capitol building and the Washington Monument is a great place for a sculpture called Antipodes. Now, there was another famous artist from the 70s and 80s in Washington, D.C. called Yuri Schwebler. And there's an article in the Washington Post here in 1984 about him. And it says, Yuri Schwebler emphasizing forms and environments related in various ways to basic physical forces or the history of public art forms, the magnetic North Pole or the Russian constructivist was an early urban earth artist. And already, you're talking about invisible forces. It's very similar to Sanborn's work. And the writer here just goes on to say, Jim Sanborn continues to explore this evocative vein. So Schwebler's last work was in the early 80s, and he's saying that Sanborn continues that work. So there's a picture of Schwebler in 1974. And one of his most famous pieces of work was turning the Washington Monument there into a sundial. You can go and watch the video to explain how he did that, to understand how he did that, or you can read the transcript here. So he turned it into the biggest sundial in the world for a little while. And the language is very interesting here. So it talks about how he waited for it to snow and borrowed a snowplow, and then he rayed out the straight lines across the snow to plot the shadow instead of laying out, it's raying out, which is it's sort of an interesting keyword in the concept in the context of Kryptos. And he talks about artists point out things people don't see, and he talks about light and shadow. It's just very similar to the themes that Sanborn looks at. And there's another of his works, which is obviously very temporary, in 1971. So he stenciled some yellow markers there on an alley so that the shadow would be cast right down that alley at a particular time. Lights and shadow, particular angle, something between 266 and 274 degrees. And looking at sundials more generally, Sanborn did talk about Schwebler in his 6.5 hour interview. Schwebler was obviously Yugoslavian, not Russian. We could connect sundials to Berlin. The TV tower in Berlin is huge. You could easily turn that into a sundial if you had enough space around it. Berlin has Europe's largest sundial since 1985, which is pictured here in the Britzer Garden, and that would connect the themes of light and shadow, magnetism, rays in the snow, and time. And you might be able to connect it to the sundial in the Egyptian Museum as well. We need to remember that the Washington Monument himself was inspired by Egyptomania, like an obelisk. The Schwebler pieces have that theme. Where there's a YouTube video they're discussing it, and the curator says it's the interaction of light or shadow on the earth. I mean, that's pure Sanborn there. So the final puzzle of Kryptos could be something like, finding a past or future date, time and place, or an alley in Washington, D.C. when a shadow or a ray of light points east northeast. That's something like a possible idea. There's one more thing from Washington, D.C. around the time Kryptos was made, which no one's talked about. This was the largest clock in the world in the Guinness Book of Records here in about 1990 to 1995. It's called Timepiece by John Cipher in the International Square building. And it was just like Kryptos, the result of a competition. And John Cipher had the idea of making a sculpture that was also a clock and telling the time in a changing light display, which is just like the Binninger's famous clock in Berlin. And the themes of uniting time, space, and light are there. But it wasn't very successful as a clock because nobody was able to just look at it and tell the time. It was much worse than the Berlin clock in that way. There's an Odd Couple episode there with making fun of modern clocks with colored lights there, which is pretty funny. And there's another quote there from 1985. It's an electronic sundial for 12 cities around the world. Okay, so getting back to Tintin, there's the original French comic from 1934, and he's using his goniometer or his direction finder to find a radio signal, and he finds that it goes east northeast, and then he plots it on a map so you can see where that line is going from China, India, Japan. What a coincidence. So to summarize everything, the implied key for the known K4 plaintext has a very strong bias towards the early letters of the Kryptos alphabet, and if you just looked at alternate letters like even letters, that bias is even stronger. It doesn't look like a coincidence, but no one knows why. And other people have also noticed, this EYICAK, something strange is happening there. So there are possible explanations, mapping the Kryptos alphabet to linotype-like alphabets, or maybe using key letters based on differences between letters or not sums. The possibility of a transposed English key is still open, but it would be very unusual English. I don't think running key or transposed running key could be solved at this length. Definitely not at the time Kryptos was created. Plain text auto key with transposition is a bit more likely, but then again, it's already a very error-prone algorithm, and I don't think you're going to be able to find the key text by going through large amounts of books looking for transposed English. Have John le Carre referring to Kryptos in 1989. We have Yuri Schwebler and John Cipher in the 70s and 80s, inspiring Sanborn, and their work is in Washington, D.C. and very closely parallels it. So that could be, closely related to K4, or the so-called final puzzle. When you review Scheit's work, there's a lot of weird things going on. There's a story about cryptanalysis of a distillation ciphertext, which is just a Caesar cipher, which is just a very weird thing to say in a biography. And when you review historical challenges like K4, the ones that were eventually solved, they go in every direction. So there's experts who created challenges and turned them into unsolvable messes, unaesthetic ciphers. There are challenges that can't be solved without huge amounts of extra information, and creators who vastly misestimated the difficulty of their construction. And then there are a few ciphers that came together and ended up just right. Just like the code book ciphers and the Belfield ciphers, which came together in the end, like the book Masquerade. Okay, thanks for listening. See you.